Good morning. Hope everybody's doing all right today. We are going to pick up where we left off in section 2.3. So we got a couple more examples to finish up there. Then we'll get into 2.4 today. My goal is to probably get through all of that and maybe even get into some of 2.5. And then next week, we'll get into finish up 2.5, work on 2.6, and then 2.8 whenever we get there. So I've already adjusted due dates of homework at this point. So just don't forget the 2.1 to 2.3 homework is due by midnight tonight. The next homework that covers 2.4 through 2.6 will be due on Tuesday now. And then the 2.8 homework I have set for Thursday. And just expect that the test, it says it's going to be on Wednesday. Thursday probably is the earliest it would be due. So either I would post it on Tuesday night, be due Thursday. And it might even be I posted on Wednesday and it's due Friday. Okay, so just know it'll be sometime next week, but most likely not on Wednesday of next week like it says on the calendar. It'll probably be due on Thursday or Friday instead. Okay. Any questions, comments, concerns about anything before we get started? All right, so like I said, this is still section 2.3, so we're still looking at these differentiation formulas. Now we're going to look at what's called a normal line. Okay, so remember we've talked about tangent lines so far. A normal line to a curve C at a point P is the line through that point that's perpendicular to the tangent line at that same point. Okay, so what we're going to basically be doing is the same work we've been doing all along to find our tangent line. And then we know now that the normal line is just going to be perpendicular to that tangent line, but at that same location. All right, so that's all we're going to do to find the normal line now. All right, so what we want to do this time is find equations of the tangent line and the normal line to this curve at the point that's given. All right, so like I said, we're going to start out the same way. We're going to start by finding the tangent line first. How are we going to find the equation of our tangent line based off the information that's given here? So what's the first thing we would need to find? Okay, good, right? So we know the derivative represents the slope of our tangent line, so we need to find the derivative first. So let's start with this one. We're going to find y prime. So what rule are we going to have to use this time? Okay, I think Dean's got it up there. Quotient rule. Good. So we're going to use quotient rule to find our derivative here. So we're going to let the numerator be our f function. We're going to let the denominator be the g function. So I'll come over here and separate those. We'll say f is square root of x, and g is 1 plus x squared. Okay, so remember, for our quotient rule, we need the derivative of each of those now. So what are we going to do to find f prime this time? Okay, good. So it is a power rule. So the first step is to rewrite the original function. So square root of x is the same thing as what? X to the 1/2 power. Perfect. Anytime you see a square root, we can rewrite it that way. Now we can use our power rule, which is going to give us what for our derivative? Okay, so we're going to have 1/2 times x. And then what's the exponent going to be in this case? Because remember, we have to subtract 1 from that exponent. So what would that give us? Negative 1/2. Good. All right, so there's our f prime. What about g prime? It's just going to be 2x. Good. All right, so now we have all the pieces we need. So remember, our quotient rule is g first times f prime minus f times g prime all over g squared. So now I'm just going to plug in those pieces. So we start with the g function. We have 1 plus x squared times f prime, which is 1/2 x to the negative 1/2. Then we're subtracting. We take our f function. I'm just going to use x to the 1/2 here, just until we finish simplifying everything. And then times g prime, which is 2x. All over the g function squared, which is 1 plus x squared, all squared. All right. Any questions up to that point? Okay, so now we need to simplify this. So what could we do first to start simplifying? Okay, good. So let's distribute what we've got up here. So we have this 1/2 x to the negative 1/2. I can distribute that to each of the terms here. I'm going to multiply this by the 1, and then we're going to multiply this by the x squared. If I do that, we're going to get 1/2 x to the negative 1/2 plus 1/2. Remember here, we're going to add those exponents. We have a 2 and a negative 1/2. That should give us x to the 3/2 minus, and down here we can actually multiply these together, so that's going to give us a minus 2x, and then we add these exponents. 1/2 plus 1 should also give us 3/2 all over. Again, I'm just going to keep the denominator factored. 1 plus x squared all squared. All right, now once I've multiplied that out, now what can we do? Good, combine like terms. So since I have two terms that have x to the 3/2, let's go ahead and combine those. We're going to have 1/2 x to the negative 1/2. If I combine like terms here, 1/2 minus 2, that should give us a negative 1/2 or a negative 3/2. We're going to get minus 3/2 x to the 3/2 all over 1 plus x squared all squared. All right, now at that point, we don't like to keep negative exponents, right? So I've got a negative exponent in my numerator. I need to find a way to get rid of that. Any thoughts on how we could do that here? Okay, so I agree that normally, right, if you have a negative exponent, we would move it to the denominator, make it positive, we're good to go. The problem here is that these two terms in the numerator are combined with that subtraction, so I'm not allowed to just move that to the denominator, right? And I don't want to just create a fraction within a fraction here, so I don't want to just create a fraction up in the numerator. So any thoughts on what we might be able to do to get rid of that negative exponent here without just dropping it to the bottom and without creating a compound fraction up top? You could, right? Now, here's the only thing about splitting up the fraction. In this case, it wouldn't be a big deal because we're just trying to find the slope anyway. We could have actually plugged in our value way earlier, okay? But I want to get some practice with simplifying these because in a lot of cases, you're going to be setting this derivative equal to something like 0, and having it in a form where we can easily set it equal to 0 is going to be important. So I just want to make sure, right, if you split it, then it's really hard to set equal to 0 and solve for x. Okay, so I want to think of a way that we can actually simplify this, but keep it all as a single fraction also. I'll give you a hint. It's going to involve multiplying numerator and denominator by something. So any ideas on what we can multiply the numerator and denominator by here that would get rid of that negative exponent up top? Okay, it is an x, but what power of x would we need to multiply by if I want to get rid of an x to the negative 1/2? Okay, so an x squared, right? If we do that, remember when you multiply, you add the exponents. So if I multiply by an x squared up here, I'm actually adding negative 1/2 plus 2. That's going to give me a positive value, right? But it's still going to be fractional. Is there anything I could do to just get rid of it altogether? 1/2, right? Because if I multiply this by x to the positive 1/2, when I distribute that and I add it to the other exponent there, that exponent's going to cancel out completely, right? So that's what you always want to look for is you've got a negative exponent, we can multiply numerator and denominator now by the opposite exponent. Okay, so now I'm going to distribute what I've got here in the numerator. So again, I'm multiplying this x to the 1/2 times each of those terms. When I do that, now we're going to get 1/2. X to the negative 1/2 times x to the 1/2 is going to give us what? X to the 0, right? So make sure you're clear here. We're adding the exponents, and so we get x to the 0 power. What is x to the 0 power going to be equal to, though? 1, right? Okay, so we're going to be able to simplify that now, and it's just going to turn into a 1/2 when we do this. Okay, I'm going to keep it as x to the 0 for now, just so we don't forget where that came from. And then minus 3/2 x. And then what's our x going to be raised to this time if we multiply the x to the 1/2 times the x to the 3/2? It's going to be 2 now, right? Because 3/2 plus 1/2 is 2. So we get x squared all over. And then down here, we're just going to have x to the 1/2 times 1 plus x squared, all squared. Now, I'm going to go ahead and go back and do this too. Since I've got these fractions 1/2 and 3/2, what could I multiply the numerator by also to get rid of those fractions? 2, right? So I'm going to come back over here, and instead of just multiplying by x to the 1/2, I'm also going to multiply by a 2. And when I do that, 1/2 times 2 just becomes a 1 there, and then 3/2 times 2 becomes a 3 here. We also have to multiply the denominator by 2, so I get a 2 down here now. Not a necessary step, right? But it does get rid of those fractions in the numerator at least. All right, now like we said, x to the 0 is just going to become a 1 here, so we're going to get 1 minus 3x squared all over 2x to the 1/2 times 1 plus x squared squared. So if you were finding the derivative for a problem like this, and I ask you to, get it in simplest terms, that's what I would basically be looking for, right? Don't leave fractions within a fraction. Don't leave any negative exponents. And so these are the steps we could go through to get it to that point. Any questions about finding the derivative? All right, now, once we have our derivative here, we're still looking for the equation of the tangent line and the normal line. What do we need to do next if we're looking for the equation of the tangent line? Good. We're given an x value of 1 right here, so we can plug in that value to find the slope at that specific point. So I'm going to take my derivative down here. I'm going to find f prime of 1. So we're going to have 1 minus 3 times 1 squared over 2 times 1 to the 1/2 times 1 plus 1 squared, all squared. So just everywhere you see an x in your derivative, we're substituting that 1 from the point that's given. All right, now we just need to simplify this. So if we do 1 minus 3 times 1 squared, what's the numerator going to be? It's going to be a negative 2. Good. Over. And then down here, we've got 2 times 1 to the 1/2. Well, that's just the square root of 1, which is 1. So that's 2 times 1. And then 1 plus 1 squared, that's going to give us a 2 squared. And so what's all that going to simplify to in the denominator? Okay, so 2 squared is 4, but don't forget we're multiplying by the 2 out front here. So overall, the denominator becomes what? 8, right? So we're going to get negative 2 over 8. And what does that simplify to? Negative 1/4. Perfect. All right, so what does that negative 1/4 represent now? What did we just find? It's a slope, right? Specifically the slope of what? Our tangent line at that point. Perfect. Okay, so now we know our slope is negative 1/4, and this is the slope of our tangent line. Okay, so now if I want to know the equation of that tangent line, I'll box this off so I can put it right in here. How are we going to find the equation of our tangent line now? Point slope form. Good, right? So I know my point here. This gives me my x1 and my y1. So we're going to have y minus 1/2 equals our slope, which is negative 1/4, times x minus x1, which is just a 1 here. And again, I'm perfectly fine if you just leave it just like that. Okay, if you want to distribute and move everything to one side to get it in slope-intercept form, that's also fine. Okay, but that answer there is good. Any questions about finding the tangent line? Okay, now, based off what we just saw on the last slide, what do we know about the normal line now? Okay, good, right? So we know it's perpendicular to the line that's given, the tangent line. So we know its slope is going to be the opposite reciprocal. So we're going to flip that fraction and change the sign. And so our slope now for the normal line is going to be 4. So just remember, perpendicular lines, slopes are opposite reciprocals. So 1/4 reciprocal is 4, and then a negative, its opposite is positive. So now if we find that equation, using point slope again, we're using the same point, but our slope becomes 4. So it's going to be y minus 1/2 equals 4 times x minus 1 now. That's the only thing that changes between the tangent line and the normal line. Any questions on that one now? And just so you know, there will definitely be a question similar to this on the test where I give you a function, I give you a point, and I ask you to find the equations of the tangent and the normal lines. Okay, so find that derivative, plug in the x value of your point to get the slope of your tangent line. Once you know that, we know that the normal line is perpendicular, so flip it and change the sign to get your slope of your normal line, and then just use your point slope formula to find both of those equations. All right, 13. So at what point on our hyperbola xy equals 12 is the tangent line going to be parallel to the line 3x plus y equals 0? All right, so what do you think we're going to need to do first here? Okay, good. Let's get that equation solved for y, right? So how are we going to do that? Just divide by x on both sides. So when I do that, my equation becomes y equals 12 over x. Okay? And so now that I have my equation in that form, what do we need to do next? Okay, you could do a quotient rule. If you remember back to the examples we did towards the end of class yesterday, though, is there a way I could simplify this so that I don't have to use quotient rule? Okay, we could do a power rule by rewriting it how? Good. So I'm just going to rewrite this now as y equals 12x to the negative 1 power. Again, quotient rule would work, right? But we don't need it here, and power rule is going to be shorter. Right, so now that we have it in that form, now we can find our derivative, right? So if we find the derivative this time, what's that going to give us? Good, negative 12x to the negative 2 power. And if you want to rewrite that, remember we can bring that x to the negative 2 down to the denominator. So that's going to give us negative 12 over x squared as our derivative. All right, now that we have the derivative, what do we have to do next? So think about it this way. What does the derivative represent? Good. So we need to figure out in this case, what is the slope of the line that we want to use, right? Because in this case, we know that the derivative is the slope of the tangent line. So we just need to know what we're going to set that slope equal to now. To find that, we're going to take the other equation, we're going to solve it for y. So we're going to get y equals negative 3x. And now because we want our tangent line to be parallel to that line, what do we want our slope to be equal to? Negative 3, right? So in this case, the line that's given, the slope of that line is negative 3, and parallel lines should have the same slope. Well, now I know I've got an equation over here that represents the slope of my tangent line. I know it needs to be parallel to this linear equation that has a slope of negative 3. So now I'm just going to set that derivative equal to negative 3. We're going to say negative 12 over x squared has to equal negative 3. So again, just keep in mind here, derivatives always represent the slope of a tangent line. We know in this case we want it to be parallel to this other line, which means it needs to have the same slope. So we're going to set our derivative, which is the slope of the tangent line, equal to the slope that we want it to be equal to. Any questions up to that point? Okay, so now how are we going to solve that for x? Good. Multiply by x squared on both sides, so that'll leave us with negative 12 equals negative 3x squared. Now we can divide by the negative 3. That should give us 4 equals x squared. And then what? Take our square root. And so what are we going to get for our x this time? Plus or minus 2. Good. So don't forget the plus or minus there, so we actually get 2 different x values. Now be careful, we're not quite done yet, because what are we trying to find? Points, right? Okay, so make sure up here, we're not just solving for x, we're actually finding the points. So how are we going to find those points now? Good. So go back to your original equation, plug in the x values that we just found. Easiest place to substitute those is going to be, oops, sorry, not there, but right here where we've already solved for y, right? So I'm just going to take y equals 12 over positive 2, y equals 12 over negative 2. And so what are the y values going to be in this case? Positive 6 and negative 6. And so what are the 2 points that we actually end up getting here? Good. Positive 2 goes with positive 6. And the other point is going to be negative 2, negative 6. So those are the 2 points on that hyperbola where our tangent line would be parallel to the line 3x plus y equals 0. Any questions there? That's where I was going next. Okay, so I'm going to switch over to Desmos, and I'm going to actually show you what this looks like on the graph, just so you know how you can kind of check yourself and make sure that your answer makes sense. All right, do this. We've got xy equals 12. So there's the hyperbola. Let me actually reset this graph so that it doesn't have trig on it. There we go. So xy equals 12. Right, the 2 points that we found were 2, 6, and negative 2, negative 6. And so you can see those. I'm going to zoom out so they show up a little better. Okay, so there's our 2 points that we found. Those are definitely on the hyperbola. And then the line that we were trying to be parallel to was 3x plus y equals 0. So there's that line. And you can kind of see in this case, right, if you were to slide that line over and keep it parallel, keep it to have the same slope, it would actually pass through those points and be tangent to the curve. Now, if you want to find those specific lines, it's not hard to do. We know the points, we know the slope. So this would just be y minus 2 equals negative 3 times x minus 6. Oops, messed something up there. Slope was -3. Oh, I've got my X and my backwards. There we go. Okay, so there it goes. So it goes through that point 2,6, right? It has a slope of -3, and so that line is parallel to the original line. And then same thing with the other one. This is just going to be y plus 6 equals -3, and then x plus 2. That goes to the other point. So you can see there's our points. Okay. And then we can't get that one to come up. Oh well. Okay, so there's the 2 points. There's the parallel lines that go through each of those points and are tangent to the hyperbola. Any questions there now? And again, you'll have access to Desmos, right? And you can use a graphing calculator if you have one. Okay, so it's always a good idea to throw this stuff on a graph just to make sure your answer makes sense, right? Because if we got points that aren't even on the hyperbola, then obviously that doesn't make sense. And if you got points that were, let's say way out somewhere else, and you're like, well, wait a minute, if I get a point way over here, that slope's not going to be the same as the line that I started with. And so you'd want to go back and check your work to make sure that you're getting a point that looks like it would actually have a tangent line with the same slope. Okay. All right. So that's all for section 2.3. Let's take a look at 2.4. All right, so 2.4, we're going to look at derivatives of our trig functions now. So everything we've looked at has been, polynomial, quotients, some products, things like that. So now we're going to actually look at what happens if we take the derivative of a trig function. We're going to start with sine. Okay, so here's our sine graph. And I want us to think through what we know about the derivative of this graph first, right? So kind of like we did with that first example in the last section, where we thought about the slopes of those tangent lines and what that graph would look like. We're going to do the same thing with sine and see if we can come up with a formula for what its derivative should be. And if you already know what it is, don't shout it out, okay, because I want to actually work through it. So I'm going to come down here, and this is going to be my y prime graph. All right, so looking at that graph, they've kind of already marked out some key points that we want to focus on. So remember, one thing you always want to look for is where do we have turning points, because we know we're going to have horizontal tangents there. What will the derivative be equal to where we have those horizontal tangents? 0, right? And so in this case, where's one place where the derivative should be equal to 0 then? Okay, so, so be careful here, right? Because at pi, it doesn't look like we have a horizontal tangent at that point, right? So where would we actually have a tangent that's horizontal? Pi over 2, right? So notice here at pi over 2, this slope right here should be 0, which means our derivative at that point is going to be 0. It's going to be right on the x-axis. Where else would we have a point like that, where the derivative is 0? Okay, negative pi over 2 would be this point right here. That's another place. Good. So I can come over here and say at negative pi over 2, That derivative should be 0 there also. Okay. Where else? 3 pi over 2, right? So this point right here would be 3 pi over 2. And so if I follow this down now, 3 pi over 2 should have a value of 0. Okay, and then the last point would be down here at negative 3 pi over 2. That has a horizontal tangent. Its derivative should be 0 there. Good. Okay. Now let's look at some of these other key points. Right, so looking at the other points that are labeled here, let's start with 0. What does it look like the slope might be at 0 here? Looks like around 1, right? So notice here, it's definitely a positive value at 0 because it's going up, okay? But it looks like it's also increasing at a pretty steady rate of 1 to 1, right? So I'm going to come up here. I'm going to say, well, at 0, I'm going to have a slope of 1. Okay. What other points could we look at now? Okay, so each interval of pi, right? So let's go down here to this one, to pi. What does it look like the slope at pi might be equal to? Looks like -1, right? So in this case, it's definitely a negative because it's going down from left to right. And it looks like it's pretty much the opposite of what we got at 0. So I'm going to come over here now, and I'm going to say, well, let's let pi be -1. What about when we get down here to 2 pi? What does it look like that slope might be? Looks like 1 again, right? So I'm going to come up here and say, well, that derivative should be equal to 1. And then we can kind of see that with all these other points. This point right over here will be -pi, halfway in between here. That looks like it's going to have a negative slope of -1, so that's going to be down here. And then if I go all the way out to -2 pi, that looks like it's going to have a slope of +1. -2 pi, it's going to be up here. Now, if I were to connect those points, okay, since the original curve is a nice smooth curve, right, the derivative is going to kind of be the same because those slopes aren't going to change drastically. It's not going to be nice straight lines or anything. Okay, it's actually going to smooth out. If I connect those points with a nice smooth curve, what is that curve going to look like? Cosine, right? So notice here, we're starting at +1, going down here through pi over 2. We hit our lowest value of -1, comes back up, has a period of 2 pi, ends up back where we started, right? So that's our one period of our cosine graph. And if you want to look at the negative side, same thing. We would dip down here like this to -1, curve back up, and then we'd hit our highest value over here. Okay, but this graph right here now, y prime, is just the cosine of x. So that means the derivative of sine is cosine. Any questions there? Now, you could do the same thing with all of your trig graphs, right, and actually think through what the slopes look like they are, kind of sketch out a graph. I'm just going to give you the formulas for the rest of them, right, okay, but the sine one's a nice one to look at because it's really easy to see how it gives you that cosine graph. All right, so here it is, right, if you're finding the derivative of sine d dx, that's going to give us cosine. And again, I'll give you the slide in just a minute that has all the different formulas for your trig functions. All right, so let's see if we can find this derivative first, right, and then we'll get to that table. So if I want to find y prime here, what are we going to have to use? It's a product, right? Okay, so we're going to have to split this up into an f function and a g function. So what's our f going to be this time? And our g function is going to be x then. Good. So what's our f prime going to give us? 2x. Good. And what is g prime going to be? Good. That's what we just looked at. Derivative of sine should give us cosine. Now we've got everything we need. Y prime, remember our product rule is f g prime plus g f prime. Now we just plug everything in. Start with f. We've got x squared times g prime is cosine x plus our g function is sine of x times f prime is 2x. Okay. And we're done. I mean, if you want to rearrange terms here, you can definitely do that just so all your x's are out front of the trig functions, right? But overall, there's nothing else we can really do to simplify this. So this is just x squared cosine x plus 2x sine of x. Any questions on that one? Okay, so the new stuff here, right, is the trig function itself. Okay, but always keep in mind, right, look for those products, look for those quotients, things like that. That's going to tell you what rules you're going to need to use to find each of these derivatives. All right, so here's our table that has all the different ones in it. So derivative of sine is cosine. We already talked about that. Derivative of cosine is actually negative sine of x, right? So just be careful with that one. Okay, you do have to put the negative out front. Derivative of tangent is going to give us secant squared. Derivative of cosecant is negative cosecant times cotangent. Our derivative of secant is secant times tangent, and our derivative of cotangent is just negative negative cosecant squared x. I mean, these are just things you have to memorize. Obviously, sine and cosine we're going to use over and over and over again, right? So hopefully those just become second nature. Tangent is another one that's going to pop up a lot. It's the three on the right that we don't use as often, right? You're probably just going to have to sit down and memorize them. But hopefully, like I said, the ones on the left will use enough that you'll remember them anyway. There's no real good trick, right? It's just kind of, yeah, you got to know them. All right, and like I said, all this is in the slides, right? So if you need to go back and look at them at any point, you can find them there in the course content folder. All right, so now we want to differentiate this function and then figure out for what values of x does the graph have a horizontal tangent line. Start by just finding the derivative. So how are we going to find the derivative this time? All right, good. It is a quotient, so we're going to have to use quotient rule. So remember, f is always your numerator, so that's secant x. G is always the denominator, that's going to be 1 plus tangent x. All right, so now f prime, this just goes back to that slide we just looked at, so I'll go back so we can look at that derivative. So for secant, we're looking at this one here. So that derivative is just going to be secant x tangent x. And then our g prime, Because it's 1 plus tangent x, we know the derivative of 1 is 0, so we're just looking for the derivative of tangent this time. So again, I'm going to come over here. Derivative of tangent is just secant squared x. So that gives me my derivative here now. Again, those are just formulas you're going to have to memorize. All right, so now f prime of x. Remember, start with your g function here. So it's going to be g f prime minus f g prime all over g squared. Now we got f prime of x equals, we start with g, that's 1 plus tangent x. We're going to multiply by f prime, which is secant x tangent x. Then we're going to subtract. We have our f function, which is secant x. And we're going to multiply that by g prime, which is secant squared x. All over our g squared, so that's 1 plus tangent x squared. Any questions up to that point, finding those derivatives, substituting into the quotient rule? Okay, so now we're going to simplify. Let's multiply what we've got here first. So again, I'm going to distribute. So this gets distributed to the 1 and to the tangent. So that's going to give us secant x tangent x plus, and then we're going to have secant x tangent squared x minus, and now if I multiply a secant x times a secant squared x, it's going to be secant cubed x all over 1 plus tangent x all squared. Now, technically, that is the derivative, right? So if you got to that point just for the derivative itself, I'm okay with that. In this case, though, we're going to have to figure out for what values of x does the graph have a horizontal tangent. So what are we going to need to do with this derivative? Set it equal to 0, right? Because a horizontal tangent means the slope of your tangent line is 0. So we need to set that derivative equal to 0. That means that I'm probably going to want to do something with this numerator now to get it in a factored form where it's easy to set equal to 0. So let's look at that numerator, see if there's anything we could do to simplify it, clean it up, so that when we set it equal to 0, it's easier to solve. So do you see what we might be able to do first? Okay, good. We have a common factor up there of secant x. So let's start by factoring that out. So we're going to have f prime of x equals, if I take out the secant x, and you're left with a tangent x plus tangent squared x minus secant squared x. Denominator does not change. All right, now, secant x is easy enough to set equal to 0, right? We can do that. But still, what's left in parentheses here, not so easy to set equal to 0 and solve. So what we want to look for now is, do we have any trig identities? And I know it might have been a little while, right? But see if you can think back to your trig identities. Do we have any substitutions we could do here that would clean this up a little bit and make it easier to solve? Do you see anything in those parentheses that we might be able to substitute out? And if you don't know the exact trig identity, do you see anything in there that looks familiar that maybe there's something we can do with it to get it in a more simple form? Okay, so there's actually a trig identity, and you're going to want to just, keep these. If you've got a sheet of trig identities, or you might just want to keep those handy just so you can look for ways to simplify. There's a trig identity that involves tangent squared, secant squared. Exactly, right? That's the one. So 1 plus tangent squared is equal to secant squared. So since I see that I've got a tangent squared and a secant squared in there, I'm going to see, is there a way I could rearrange these now to make it look like that trig identity? Well, to do that, I'm trying to get tangent squared minus secant squared, so I'm going to move my secant squared to the other side. That's tangent squared minus secant squared. And now I can move the 1 back over to the other side. So tangent squared x minus secant squared x is actually equal to -1 now. So in place of all of this, I can just replace that with a -1. So now my derivative just becomes f prime of x equals secant x times tangent x minus 1 all over 1 plus tangent x all squared. Okay. So again, it's probably, for this section especially, and there might be some in the homework where you're trying to set a derivative equal to 0, and you might need to do a substitution with a trig identity to get it to that form. Okay, so just keep those trig identities handy just so you can look them up if you need to. And I promise I'm not going to give you anything crazy on a test, right? At worst case, it would be like there's a tangent and you need to plug in a sine over cosine or something like that. But for the homework, there might be some like this. All right, now that we have it in this form, we want to set our derivative equal to 0. So what are we actually going to be setting equal to 0 here? So for that derivative to equal 0, what would need to equal 0? Okay, so the derivative overall, right? So horizontal tangent, this means that f prime needs to equal 0. But if we have a fraction like that, for the fraction to be 0, what would have to be 0? Just the numerator, right? So we can ignore the denominator altogether because we know in this case for the overall derivative to be 0, the numerator itself needs to be 0. So I'm just going to come over here and say, well, that means secant x times tangent x minus 1 needs to be equal to 0 now. And that's always going to be the case, right? If you've got a fraction, you can pretty much ignore the denominator unless there's a restriction down there, right, that that can't be part of your domain, then you'd have to consider it. But in this case, 1 plus tangent x all squared is always going to be positive. And so in this case, we should be okay. All right, now that we've got it set equal to 0, how are we going to solve that now? Good. We've got two separate factors. We can set each one equal to 0. So we have secant x equals 0, tangent x minus 1 equals 0. All right, now let's think about this. When is the secant going to be equal to 0? The easiest way for me to think about this is to think about the graph of secant. So think back to your graph of secant. Where does that graph cross the x-axis? So I'm going to switch to Desmos. I'm going to show you this graph. So y equals secant x. But where is that graph equal to 0? Nowhere, right? Okay, so in this case, there are no solutions to secant x equals 0, so we can just ignore that part of our factors, right? Okay, so since the secant x graph never crosses the x-axis, it's never equal to 0, we know there's no solution to that part. All right, so this over here, no solution. So now let's look at the tangent x minus 1 equals 0. How are we going to solve that? Good. Tangent x equals 1. So again, we need to think about where would the tangent be equal to 1 now? We're taking the arc tangent of 1. Pi over 4 is one place, right? So we're going to get x equals pi over 4. But remember, because tangent is periodic, right, where else would that happen? Okay, 5 pi over 4 would be another place. And so how would we write this solution then? Okay, good. So we're going to have to say plus pi times n, or pi times k, or something like that, where that n or k value represents a constant, an integer value. Okay, so it's all the pi over 4s plus some multiple of pi. All of those locations, because this is periodic now, it's going to give us a horizontal tangent. And so this is our solution for this one now. Any questions on that? Okay, so I'm going to actually show you the graph, okay, because again, I think it's always a good idea, right, just to kind of check yourself and make sure your answers make sense. So our original function this time was secant x over 1 plus tangent x. That's what our graph looks like. I actually put trig values on this graph instead. So from negative 4 pi, 4 pi, we'll step by pi over 4. So now we said that pi over 4 should be a horizontal tangent, right? Well, that's this value right here, pi over 4. And then we said that every time we add a multiple of pi, we should have another one. That would be 5 pi over 4 would be the next one. If we add another, that should be 9 pi over 4, 13 pi over 4, and so on. And if you subtract pi, that's negative 3 pi over 4, negative 7 pi over 4, and so on. So all of those turning points there where we would have horizontal tangents, and it is the pi over 4 plus multiples of pi that gives us those horizontal tangents now. Any questions on that one? Okay, let's take our break. Okay, so 11 o'clock now, so 11:05 we'll get started back and finish up 2.4. All right. So Example 3. So we have an object here at the end of a vertical spring that's stretched out 4 centimeters beyond its rest. This should be position. Sorry. Change that. And released at time t equals 0. Okay, so its position at time t is this function here, s equals f of t, which is 4 cosine t. We want to find velocity and acceleration at time t, and then we're going to look at the graphs of these just to kind of think through what's actually happening in this scenario. Okay, so if we're given the position function s, how would we find velocity? Derivative, right? So remember, the velocity is just the first derivative of our position function. We're finding s prime. And so what's the derivative of 4 cosine t going to give us? Okay, so think back. What's the derivative of just cosine? Negative sign, right? Okay, so we know that's going to give us a negative sign. Then we can keep the coefficient, the 4. So this is 4 times negative sine t in this case. Or just negative 4 sine t. We don't have to use a product rule or anything, right? Because the 4 is just a constant. Okay, so we just keep the 4, take the derivative of cosine. That's going to give us negative 4 sine t. Any questions on that derivative? Okay. Now, I also want to find acceleration. How are we going to find acceleration? Find the derivative of what we just found, which is the second derivative of position. Perfect. So we're finding the derivative of v, same thing as s double prime. And so what's the derivative of that velocity function going to give us? Perfect. So we keep the negative 4. That's our constant. We're taking the derivative of sine, which is just cosine. So we get negative 4 cosine t. Okay. Any questions just on finding the velocity and acceleration functions here? Okay. So now, like I said, let's look at Desmos. I'm going to graph all 3 of these. We'll start with just one at a time, right? And then we'll kind of look at them all together to see how they're all related. All right, so our original function here, our position function, we had 4 cosine, and I'm going to use an x here just so Desmos graphs it. That's what our position function looks like. And I'll go ahead and graph the other 2, and then I'll turn off 1. So we have negative 4 sine of x, and y equals negative 4 cosine x. So in order there, the top one is our position function, the next one is our velocity, and then the last one's our acceleration. So if we start here, and remember we said we're taking this spring, we're stretching it out beyond its rest position, right? So 4 centimeters beyond. So that's this starting position right up here at time t equals 0, because remember the horizontal is going to be our time axis this time. Once we stretch it out, we're going to let it go. Well, what's going to happen when we let go of that spring if we've stretched it out beyond its rest position? It's going to shrink, right? So it's going to compress, right, back down towards its resting position. And so that's what you can see here with the start of this graph. So if we start up there at positive 4, okay, it's compressing now towards its rest position, Its rest position then is actually going to happen right here. So again, it's starting up here at 4 centimeters beyond its rest position. It's going to compress. Now, once it gets to its resting position, what happens? Think about if you had a spring, right? Think about what its resting position would look like. Okay. So it's not expanding again yet, right? So think about, if you're holding a spring vertically, right? Its resting position is going to be somewhat stretched out, but not stretched out as far as possible, right? So we're stretching it out beyond resting position and we're letting it go, right? And eventually, when we let it go, sorry, I'm probably let it go from the bottom, it's going to pass through its resting position. And because it has some inertia to it, right, it's going to actually compress beyond that till it gets somewhere up here. So that's what's actually happening now with this bottom part of the graph is it's compressing beyond its rest position. And then eventually what happens once it gets to a certain point? And that point that I'm referring to is this point down here. Okay, so we've stretched it out, we've let it go, it comes up here, it gets to this point, and then what happens once it gets to that point where it's fully compressed? Well, that's why. So it's done that, right? That's the pi -4, right? So that it's compressed way beyond its resting position, right? But then once it gets to a certain point where it can't compress anymore, then what happens? Then it bounces back, right? And so it's going to move back towards that resting position. And so that's what we see on our graph as it moves back towards this point here. Okay, so we've stretched it out to 4. We've let it go. Because it has some inertia, it goes beyond its resting position, which is at pi/2. It goes all the way to this point at pi where it compresses as much as it can. And then it starts to expand back out towards resting position. Now, obviously there's going to be other factors involved, right? Okay, it can't keep doing this over and over and over forever. Okay, but that's what this graph is kind of showing us, right? And so if you zoom out, it's basically oscillating back and forth now between this fully stretched out version, fully compressed version, and then back and forth through that resting position over and over and over again. Okay, that's what we're seeing here. So any questions about the position? Yeah, so if you had like a vacuum, right, or you had no gravity, things like that, those are the things that are going to affect it. And so if you took a physics class, you would actually factor in all those things and you get a much more complex function than what we have here. Right, so this is a very simplified version of what's going on, okay, but it's more just to kind of relate what's happening between position, velocity, and acceleration. Okay, but eventually, yeah, in the real world, this thing would have to taper down, right? Because eventually it's going to stop at its resting position. Okay. Now, let's think about velocity, right? So I want to just start by looking at the velocity function on its own, right? And then I'll look at position and velocity together. So at our starting time, what is the velocity going to be when we start this experiment? If we've stretched it out fully, what's our velocity? Before we let it go. So how fast is the spring moving before we let it go? 0, right? It's not moving at all. So I've stretched it out, right? I haven't let it go yet. So at time t equals 0, that's where we're starting. Our velocity is going to be 0 there. Okay? Now, as soon as I let it go, what's going to happen to the spring just in terms of its speed, right? So let's start there. What happens when I let go of that spring? Is it speeding up or slowing down? Speeding up, right? Okay, so just in terms of speed, speeding up. But remember, velocity has both a speed and a direction, okay? So we have to consider now that we've stretched it beyond its resting position and we're letting it go, which means now that it's moving towards its resting position, okay? And that's why we end up with this negative velocity down here, right? So it's speeding up as we go from 0 to pi over 2, but it's moving in a negative direction. Then once we get to that point there, right, as soon as we do that, and let me turn the position function on so you can see where that happens, okay, that point is the same as the resting position point of our position function. Okay, so this point here, pi over 2, and this point down here, where we've kind of maxed out our velocity in the negative direction, that is the resting position. So we've let it go. It's moved up here, right, halfway to its resting position. That's as fast as we're going to be moving. Because then once it passes that rest position, what happens to the spring as it compresses more? Just think about an actual spring in your hands, right? If you stretch it out and you let it go, once it gets beat, it starts slowing down, right? So as it approaches that fully compressed mode, right, it's going to slow down as it gets towards the top. And that's what we see happening over here now from pi over 2 all the way to pi, right? It's still moving in that same direction, right, the negative direction, but the velocity is not as much as it was before. Okay? So it reaches that maximum velocity in the negative direction, okay, when we get to pi over 2, and that's where it reaches equilibrium, right, the resting position, and then it continues on. Now, where it gets right here, velocity equals 0, that's where our position is right here now, right? So as soon as it gets fully compressed, what happens to the spring in terms of velocity? So if the velocity is the black graph here, and the blue graph represents now that it's fully compressed at pi, what happened to that velocity? The velocity. Okay, it does. It shifts to the positive, right? I agree with that. But at that split moment of time at pi, what is our velocity? Again, the velocity here is the black graph. It's 0, right? So if the velocity is 0 there, that means that the object actually stops. For a split second, right, as it compresses, it gets to a point where it can't compress anymore, and the spring actually stops. Then it switches direction and starts falling back in the other direction. Okay, and so that's what we actually see here at pi, where it switches from being negative to being positive, is there is a split second, and you can see it on the position graph too, where it reaches that bottom point where the velocity is 0, the object stops, and it switches direction. Okay? Now, in general, if you're stretching out a spring and you let it go, you're not going to see that happen, right? Because it's just going to keep oscillating back and forth so fast that your eyes aren't going to pick up on it. Okay, but there is a moment in time there where when it reaches the top, it actually stops before it changes direction and starts falling. Okay, and then if you look at the other side, okay, we can kind of see the same thing happening over here now. It's traveling in the positive direction, speeding up now, which means now it's falling beyond its resting position, expanding back out to where we had stretched it. And then once it reaches a certain point, right, then it starts slowing down again. That's where it passes equilibrium, and it goes back to a velocity of 0. That's where it will be fully stretched out again. And that's from 0 to 2 pi now, that full period of our trig function Okay, that's what we've got. We've stretched it out, we've let it go, it fully compressed, it expanded back out to where we started. Okay, and at 2 moments in time where it was fully compressed and where it's fully expanded, okay, that's where our velocity actually is 0 and the object stops moving altogether. Okay. Any questions there? Okay. Now acceleration. Okay, and so this is the really tricky one to kind of see and think about now, because you have to think of it in terms of position and velocity kind of at the same time. So notice here that our acceleration actually starts in the negative. Okay. But that acceleration is increasing, even though it's negative here, it's increasing all the way from 0 to pi. And the reason for that is that our position and our velocity are moving in the same direction. Okay, so since the position is going from positive towards the negatives, it's decreasing, and the velocity is also decreasing there, right? It's in the negatives. We know in this case that our acceleration is actually increasing. Okay? And eventually, we're going to get to a point where that velocity is 0 at pi, where it starts to decelerate, right? So the acceleration starts to decrease, and that's where it starts moving in the other direction. Okay, now, I'm not terribly concerned, but I know that a lot of you are going to go on to take Calculus 2 in physics, okay? And so seeing things like this and how these things are related, it will be important as you move on to that, right? But again, those functions are going to get even more complex than what we see here, but just understanding those relationships, okay, will be important, all right? But for us, the main thing is know the relationship now. To find the velocity, you take the first derivative. To find the acceleration, it's the second derivative. And knowing how to do that with trig functions is especially important, because those are the types of functions that actually come up a lot, especially with this oscillating motion, these types of problems. Okay? All right. Example 4. Now we want to find a 27th derivative of cosine. All right, so we definitely haven't gone that far with any of our derivatives so far. So what do you think we could do here to find our 27th derivative of cosine? How would you start? What would you need to find first? All right, good. Let's start with the first, right? So let's go with our first derivative. I'm going to say f prime. What would our first derivative of cosine give us? It's going to be negative sine, right? So that's just using our formula. Now we have negative sine as our first derivative. Let's go ahead and find the second derivative. What's our second derivative going to be? Good, right? So the derivative of sine is cosine, but this one's negative, so it's going to be negative cosine. Let's keep going. Look for third derivative. What's our third derivative going to give us? It's going to become sine, right? Because when we take the derivative here, we have the negative, but the derivative of cosine is negative sine. And so overall, this is going to become a positive sine of x now. Okay, what about the fourth derivative? And remember, we use parentheses there to represent that derivative. We get 3. Good. Derivative of sine is just cosine. So we get cosine x. Well, what's going to happen then if I take the fifth derivative? It starts over, right? It's the same thing as f prime. So in this case, whenever you have one of these sine or cosine functions, you're going to get these repetitions in what the derivative is. So if you're trying to find the 27th derivative, we don't actually have to go all the way to 27. We can just figure out where we are in that pattern, and that'll tell us what that derivative is. So in this case, where would the 27th derivative land? So if cosine is the fourth, and then we're back to negative sign with the first, where would we hit the 27th derivative? At the third derivative, right? So think about it this way, this is going to be the fifth derivative. It's going to be the sixth, seventh, and eighth. So basically all multiples of 4 now are going to give us cosine, which means that f, the 28th derivative, is going to give us cosine of x, and the 27th derivative, sorry about that, is going to fall right here before that one, right? So it's going to be the same as whatever we got for the third derivative. So the 27th derivative then is going to be equal to sine of x. So again, that's always going to be the case, right? So just figure out, based off of whatever you're starting with, right? Because if you start with sine, it would be a little different. Okay, so find those first 4 derivatives, and then we just know it's going to repeat after that. So you just have to figure out where you are in that repeating pattern. So for the 27th, we're going to be the same as the third. Any questions on that one? All right. Now some limits. Okay, so limits with trig functions. The limit as theta approaches 0 of sine theta over theta is always going to be equal to 1. Okay, so we can't do a direct substitution here, right, because that would give us 0 in the denominator. Okay, but this is just a formula that we can always remember and make sure here it's as long as the value inside your sine function matches the value in your denominator. Okay, that's what we have to have there. If that's the case, then this limit is going to be equal to 1. Okay, and then if we have the limit as theta approaches 0 of cosine theta minus 1 over theta, again, whatever's inside your cosine has to match the theta in the denominator, then that limit is going to be equal to 0. So what we're going to be doing now is looking at some limits that involve these trig functions, trying to get them into a form that looks like one of these two, so that then we can do that substitution for that limit. All right, so let's take a look at this one. So we're looking for a limit as x approaches 0. We have sine of 7x over 4x. Like we said on the previous slide, whatever's inside the sine function needs to match the theta value, or in this case, the x that's in the denominator. That's not the case here. So we need to try to make those look the same so that we can actually apply that property that we just saw. What would I have to do to 4x to make it look like what's inside the sine function now? Okay, so multiplying by 7, right, if we did that, that would give us 28x, right, which would not be the same as what's inside. If you're on the right track, what would we actually want to multiply by, though, if we want to make it look exactly like what's inside the sine function? Seven fourths, right? So we're going to multiply here by 7 over 4, but whatever we do in the denominator, we have to make sure we do the same thing in the numerator. I'm going to multiply by 7 fourths up top also. So now we're going to get the limit as x approaches 0 we're going to have 7/4 times the sine of 7x over, and now 4x times 7/4, the 4's cancel out, and now we have the 7x that we were looking for there. Again, the goal here is to make whatever's inside the sign match whatever's in our denominator. Now, at that point, remember we have a property of limits that says if we have a coefficient, we can do what with it? Pull it out, right? So I'm going to rewrite this now. That's 7/4. I can bring it to the front. So we're going to have 7/4 times the limit x approaches 0, sine of 7x over 7x. Now, what is that limit going to be equal to? Just the limit part. 1, right? Because we've matched up what's inside the sign in the denominator. So now I have 7/4 times 1 using that property from the last slide. And so this overall limit should be equal to 7/4. Any questions on that one? All right. So we're going to stop there for that section, okay, because I want to get into 2.5 and show you the chain rule at least a little bit today. Let's move on to that. And this way, if you want to work on some of this homework over the weekend, you should be able to now, okay? All right, so the chain rule. So this is another rule that we have to remember when we're finding derivatives, specifically when you have the combination of multiple functions, okay? So if you have like an f of g of x type of function, that's when we're going to have to use our chain rule now. All right, so if g is differentiable at x and f is differentiable at the g of x function, which is the inside part, then the composite function, big F, which is f of g, is differentiable at x, and f prime, big F prime, is given by this product. Now, I'm going to write this a slightly different way because I think it's just a little bit easier to understand what it looks like. I'm going to use u equals g of x here, and I'm going to say that our derivative now for big F of x is going to be equal to f prime of u times u prime. So in other words, we're finding the derivative of the outside function, keeping what's inside the same, and then we're multiplying by just the derivative of the inside. Okay, it's the same thing that's written up here. We're going to do what's called a u substitution, where u is the g of x function, and then we're going to use that notation to actually find our derivative now. Okay. Again, this only applies if you have a composite function where you have an inside and an outside, and that's when we have to use chain rule. All right, so let's look at this one now. So we have big F, we want to find big F prime if f of x is equal to the square root of x squared plus 1. Okay, so first thing I'm going to do here, let's identify what the inside part is. Okay, so if we have the square root of x squared plus 1, what could we let our inside function be equal to this time? Good, the x squared plus 1. So I'm going to say u equals x squared plus 1. Now I'm going to rewrite the original function in terms of u. So I'm going to rewrite f of x as the square root of u. Now, if I want to find that derivative, what would I need to do now? Just for the square root of u piece. we use a power rule, right? So we can rewrite this now as f of x equals u to the 1/2 power. So anytime you see a root like that, change it to a fractional exponent, and then we can just use our power rule. So when I find my derivative, we're going to have f prime of x is going to be equal to what? Good. We bring out the 1/2. We keep the u. We subtract 1, which gives us negative 1/2. But because it's a chain rule now, the only additional thing we have to remember is that we're multiplying this by u prime. So whatever the derivative of the inside was. So we do our u substitution, find your derivative just like you always would, and then we just have to remember this extra little piece down here, we have to multiply by the derivative of u. Which means I'm going to come back over here to where I found my u value, and I'm going to find its derivative. What would the derivative of u be equal to this time? 2x, right? Now I have all the pieces I need. Now I can just go back and substitute. So f prime of x is going to be 1/2 u, which is x squared plus 1 to the negative 1/2 times u prime, which is 2x. And make sure that you actually go all the way back to your x value, since that's what the original function was in terms of. Okay, so once we find our derivative in terms of u, just do those substitutions to get everything back in terms of x. Now we can just clean this up. So we have 1/2 times 2. Those are actually going to cancel, and we can move this negative exponent to the denominator. So we're going to have an x in the numerator, and then we're going to have this x squared plus 1 to the positive 1/2 in our denominator now. So that's how chain rule works. Okay, so if you have a composite function, a function inside another function, pull out the inside function, let that be your u, take your derivative with respect to u like you always would, but don't forget to multiply by the u prime. Okay, so we have to make sure we find that value, then get everything back in terms of x, and then we're good to go. Any questions there now? All right, let's take a look at these. So same thing, we have sine of x squared. First thing we're going to have to do is identify what is our inside function. So what do we want to let u be equal to this time? Okay, so if the entire thing was going to be, it is going to be sine of u, right? If we rewrite it, which means that our u value is going to be what though? X squared, right? Okay, so we're letting u be equal to the inside, which is the x squared. Any questions about that step? Okay, now if I find my derivative, what's the derivative of sine of u going to give us? Good, right? So derivative of sine is just cosine, so we get cosine u. But because it's a chain rule now, we just have to remember to multiply by u prime. So now we can go find our u prime value. What's the derivative of u? 2x, good. And once we have everything we need, now we can just substitute it back in. So we're going to get y prime equals cosine of x squared times 2x. And again, that answer is perfectly fine if you want to rearrange your terms just to get the 2x out front of the trig function. That's fine also. And either one of those answers is perfectly fine by me. Any questions there? Okay, let's look at the next one. We have sine squared of x this time. So not the same thing as sine of x squared. What's our inside function going to be this time? Good. So we're going to let u be equal to sine x. So when I rewrite this now, in terms of u, what is our function going to look like? U squared, right? Because that's what we're doing is we're squaring the sine of x, so it's just going to become a u squared now. Now we can find our derivative. So what's the derivative for u squared? Okay, 2u. Good. And just don't forget, because it is a chain rule, we have to multiply by the u prime. Now, if we're looking for the derivative of u to substitute in here, that derivative is going to give us what? Cosine. Good. So now we have all the pieces we need. So we're going to have 2 times sine of x times cosine x. And so 2 sine x cosine x, perfectly fine. That is actually a trig identity. So if you wanted to write it as sine 2x, that would be equivalent, right? Okay, but again, that answer there, 2 sine x cosine x, is perfectly fine. Any questions on that one now? All right. Now, the power rule combined with the chain rule. Okay, so basically, this is just, it's going to work the same, right? But it's kind of showing you a shorthand. It's saying that if you have something like u to the n, we can just bring out the n, subtract 1 from the exponent, and we just have to remember to multiply by the derivative of the inside. So if you don't want to write out that u equals over to the side every time, we could follow this formula, right? But don't stress too much about all this notation, because to me it just gets more confusing than it needs to be. But we can use a chain rule with a power rule if that's what we have, okay? And that's what we have here. So y equals x cubed minus 1 raised to the 100th power. We have an inside function being raised to a power now. Now, I would say early on, I would probably always do my u substitution just to make sure I know what I'm doing. Eventually, you might be able to do some of those steps in your head, right, and kind of skip some stuff. That's perfectly fine if you get to that point. What are we going to let u be equal to this time? Okay, so it is going to be u to the 100th power, which means our u value is what? Good. The inside x cubed minus 1 now. Any questions about finding the u value or rewriting the function in terms of u there? Okay. Now, if we find our derivative, what is our derivative going to look like? Good. 100 u to the 99th power. And again, because it's a chain rule, just don't forget, we got to multiply that by u prime. Now we find our u prime. So what is u prime going to be this time? (3x squared). Good. Come back over here, substitute everything back in. We get 100 times x cubed minus 1 to the 99th power times 3x squared. Now, I would at least go ahead and multiply the 100 and the 3 together here. And if you want to move that x squared out front, we can do that too. So this is going to give us 300 x squared times x cubed minus 1 to the 99th power. Okay. And again, all the last slide was trying to show us was if you want to get to a point where you don't have to write this stuff out over here every time, we're just using power rule, and then we just have to remember to multiply by the derivative of the inside. So we bring the 100 out front, keep what's in parentheses, drop the exponent by 1. That's what gives us this 100 x cubed minus 1 to the 99th. And then we multiply by the derivative of x cubed minus 1, which is just 3x squared. That's where this piece comes from. So again, if you want to start doing it that way, right, if you can see it, that's fine. But there will be some where, the inside functions get a little trickier. Those derivatives get harder to find. You're probably definitely going to want to show that work out to the side for those problems. Any questions on that one now? Okay, so that should at least give you a start. I'm not going to do example 4 because I think it'll take me longer than the couple minutes we have left. We'll pick up with that one next week. We'll finish up all the chain rule problems then. But again, you should be able to at least get started on the 2.4 and some of the 2.5 homework. Send me questions. If you work on that over the weekend, send me those questions in WebAssign as you have them. Again, that homework is due by midnight on Tuesday. The 2.1 to 2.3 stuff, though, if you haven't finished that already, that is due by midnight tonight. So make sure you get that done. And again, the test will most likely be due on Friday of next week is what I'm thinking right now. Maybe Thursday at the very earliest. But we got to finish up, the rest of this unit. So it'll probably take us at least 2 days, if not 3 days next week to do that. Okay. Planning on that being due either Thursday or Friday of next week. Okay. We're going to go back to the trig thing we didn't finish. So what trig thing that we didn't finish, Dean, are you referring to? Yeah, but we had covered everything. There was only one other example there. So if you want to go back and review that one, it's in the text. But I'm just not going to go back and do that specific problem. If you've got questions about how to do one like that in the homework, just send me a question. I'll be happy to explain it. But yeah, we covered the formulas, right? And we did one example, so I'm not going to do that other one. I'll go ahead and post the practice test today as soon as we get done. That way, if you want to start looking at that before next week, you can. Okay. Any other questions? Yeah, Paulina. So I was just saying, I'm going to post that as soon as we're done here today, and that way, if you want to start looking at it over the weekend, you can. Okay. I'll get the practice test up. Any other questions? All right. If you think of anything else, just let me know. Otherwise, have a great weekend, and I will see you all on Monday.